Okay, so this exercise is our final example for application of the hydrostatic equations. So as you can see, the problem in here, we have two conditions. The first one, the condition in here, we only have the planar gauge. And the second one is the curvature gauge. Okay, so we have two conditions. The first one is the planar, and the second one is the curvature gauge. Okay, so as I mentioned, if you would like to do the exercise like this example, the first one you need to compute how large of the pressure force, and then the second is the location of the pressure force. Okay, that's what we call that is the CP point. So the first one, we need to extend the planar to find out the point crossover with the liquid surface, and then we call that the zero point in here. So we have a zero point, and then you need to see the length along the vertical in here is the 4/L, and because the degree is 45 degree, so we actually know what the length in here. So you need to compute the length in here, in this length. So we know that the length in here is the 4/√2L because the 45 degree in here. Okay, so right now we can compute some important information. The first one is the point, the centroid point for the plate in here. Okay, so we need to compute the length from the liquid surface to this point, because we would like to compute the pressure force. So the pressure force Fp is equal to the gamma. Gamma in here, we put the plate in the liquid, but we didn't know what the liquid material. So in here, I use the gamma. The example didn't tell you the liquid is water, so we cannot directly use the water gamma W. So I use the gamma in here, and we have the Z bar. The Z bar is the yellow line, the length of the yellow line. It indicates the depth from the liquid surface to the centroid point, the depth, the liquid depth, and the total area of our planar plate. Okay, so in here, I know that what is the length along the vertical line. So you know that in here, the Z bar should be equal to the 4/1L, this length. And how about the length in here, the buttons? So we actually know this is the length in here is the 2/L. It's the 2/L. So you can maybe I use the symbol in here LZ indicate the length along these directions. So we actually know we have the 2LZ is equal to 2/L, and the angle in here is maybe in here is the 45 degree. So you can directly use the cosine 45 degree. You have the LZ. Okay, so we need to plus the LZ in here. So you can compute the LZ. So in here is 2 root 2 over 1 L. Okay, 2 over 1 L. So the D bar is equal to the 4 over L plus the 2 root 2 over L. So you can compute the number in here. So I compute first 2 multiply the root 2 and over 1 and the plus the 1 divided the 4. So this is around the number in here is 0.604 L. Okay, and then what are the areas? What are the area in here? So we actually know the example tells us this is the planar gauge with the length L and the width W. So we can directly compute the area of the plate is L multiply W. So we put the number, go back to here. We have to keep the gamma in here. And the D bar is 0.604 L. And the area is the L W. So reorganize the equation here is 0.604 and the gamma W L squared. Okay, this is our pressure force. So the second question is where the pressure force, the acting point of the pressure force. So maybe I put the points in here. In here, maybe this is the CP point. So we know that the force, the pressure force acting on this point, FP acting on this CP point. So we need to find out the CP value. So because we didn't know the CP, the length. Okay, so we know that the YCP along this direction is the Y directions. So the YCP is computed start from the 0 point to the CP point, the length, and minus the Y bar. What is the Y bar? Y bar is the Y length from the 0 point to the centroid point. So the YCP minus Y bar, we know that is equal to the I, the second moment, okay? The second moment divided the total area and divided the Y bar. Divided the Y bar. Okay, so right now we need to compute the I. What is the I? The I is the second moment of the plate. And then we know that the plate is a right angular plate. So, and the rotation axis is into the paper. Okay, rotation axis is into the paper. So we know that the second moment is 12 over the width. The width. The rotation axis direction is parallel to the width into the paper. So we use the W and then the L is the cubic power. The cubic power. Okay? Because the rotated axis is parallel to the width directions into the paper. So the W here, I only use the 1 power. But the L, I use the cubic powers. And what is the Y bar? The Y bar, we know that the length in here, is 4 over root 2 L. And the length in here is 2 over L. So the Y bar is equal to 2 over L plus 4 over root 2 L. Okay, so you can compute the number in here. So the root 2 divided the 4 plus the 0.5. So it's around the 0.853 L. Okay, so I can put all of the number go back to here. So the first one, I is omega L cubic power 12 divided the total area is LW over 1, and divided the y bar is 0.853 L over 1. So I can cancel out some parameter like the L, and here only 1 powers, and the W. So what is the YCP minus the y bar is equal to the 1 divided the 0.853 and divided the 12. So it is around the 0.0977 L. Okay. So because we have the FP and we have the y minus the y bar, so I just remove here. We reconsider our questions. The question is what is the magnitude of the reaction force at the point A? So we have right now we already know. We have the YCP point here, and there is a FP, and here is a reaction force A at the A point, and we can convert the reaction A point to these directions. We call that the FA. Okay, so we can have the moment balance between the FP and the FA force. So we know that the FP multiply the L from the B to CP along this length. So this is a BCP. The line in here is the length is a BCP. Okay, and multiply the FP multiply L BCP will equal to the FA multiply the total length is the L in here will balance the moment balance, and we can rewrite the FA by the RA reaction force at the A locations multiply because the degree in here is the 40. It's a 40 degree, so you can multiply the cosine 45 degree and multiply the L. Okay, so the answer is, what is the RA value in here? What is the RA value in here? So we actually know the FP, the answer in here, and we know that the YCP minus the y bar, the YCP minus the y bar. So the FP, I put the number inside. FP is 0.604 gamma WL squared. This is FP multiply LBCP. LBCP is equal to the 0.0977 L plus the length. This is a half. The length in here is the 2 over L. So we plus the 0.5 L will equal to the RA. The cosine 45 degree is equal to the root 2 over 1 L. So you can find out the final answer for the RA values. Okay, so you just based on the moment balance, and you can compute the final answer. So I directly write down the answer in here. So for these questions, you can understand what the reaction force. The reaction force is the functions of the gamma. It depends on what kind of the liquid you use. And depends on the length and the width of your plate. Reaction force. So for the engineering design, if the reaction force is smaller, will be better because we would like to open the gauge. If the reaction force is larger, we need more force to require to open the gauge. Okay, so for the designer, we need to reduce the reaction force based on our design. So the second question is in here. For the curvature gauge, the figure B, will the magnitude of the reaction A be greater than, less than, or the same as that for the planar gauge? So for these questions, the answer we don't need to compute again. So I just highlight the answer. For the condition 2 in here, the reaction force will less than the condition 1. The condition 1 is the planar gauge, but the condition 2 is the curvature gauge. So the reason why the second condition for the curvature gauge has the smaller reaction force compared to the condition 1, that's because above the curvature, the water loading, the liquid loading is smaller because this is a curvature shape. But in this condition, the above liquid loading is larger compared to the condition 2. Okay, that's why we don't need to compute again because we can directly to see the two conditions above the gauge, how much liquid loading we have. So we just pick up the liquid loading smaller one, and this is our final solution. OK， 这个很重要，就是我们在静力学里面，流体静力学里面，你只要去判断你的 liquid 的 loading 比较小的，那可能是对你比较好的，因为你不需要花太多力气去打开这个闸门。那平面跟曲面，大家从两个案例可以很清楚看到，下面的曲面的上方的 liquid loading 其实是比较少的。那当然我就不需要太大的力量去打开这个 gauge。OK， 所以我们这个的话就不要再去重算那个 curvature 了。当然你们也会去算曲面的嘛，可是实际上我们去算平面，只是想要让你再复习一下。那曲面就会告诉你说不用再算了，因为它的 liquid loading 就比较少。OK。So because of the time limitation, so I don't need my calculator to compute the final answer. But you can double check when you go back home. Okay? So for our class, each chapter, some material will related to the laboratory experiment. Because the next semester, we have the laboratory experiment. And because this is one of the experiments in next semesters related to this topic. So we call that we have the hydrostatic experiments, and this is our device. You can see the device in here. And the next page, we have the cartoon figures. So actually you can put the water inside the machine. You can put the water inside the machines. And then you have a different water line. You can have a different water line. And then in conditions in here, we have the height, D, and the A length in here. And then we put the water inside. So in the condition when the Y smaller than D, the Y smaller than D, and you can follow the force. This is the pressure force, and the YCP is equal to 3 over Y. And because you have the F and you have the YCP, so you can compute the moment by yourself. And this machine will have the mass. You have the mass in here, and the mass will put the weight downward, right? And we have the hinge in here, and the L is the length between the weight and the hinge. So we can compute another moment. We call that is the experiment moment. It's equal to the mg multiply the L, right? The mg multiply the L. So you can put the different water inside, and you can have the different mass balance. The mass, where is the mass? There is a recorder. We have a recorder in here, and the recorder will show maybe 1 kilogram or 10 kilogram in here. So you can read the digital weight from the machines, and you can compute the mgl numbers. So this is our experiment moment. And the left-hand side in here is the theoretical moment. You can compute when you understand the hydrostatic equations. Okay? So the second condition is when the water height is larger than the D. When the water height is larger than the D, and you need to base on different equations to compute the pressure force and the YCP. And again, you can compute the theoretical moment. And the right hand side, you can have a recorder show the mass here, so you can compute the mgl. So for this experiment, we need to compare. We compute the theoretical moment and the empirical moment, and then we compare the difference. Okay, and you can see the difference sometimes is quite large, and sometimes is smaller. Okay, so this is in next semester, if you take my class for the laboratory experiment, sometimes we just do the experiment and write down some number in the table and compute some theoretical, and that means the true condition and the theoretical condition, and then you compare each other. Theoretically, the two numbers should be the same, but in practical, they are not the same, right? So we need to discuss why they are different. OK， 那我们这堂课就是每次如果上到一些跟我们下学期做流力实验有关系的课的内容的话，我们就会稍微讲一下。等到你们下学期做实验就是这样，每学期都是一样。你这学期修了流体力学，到下学期去修实验课的时候，你就想说这个实验到底跟我学流体力学有什么关系？如果你会产生这个疑问的时候，你就要打开这个 PPT， 大概看一下，因为其实都有一些答案在上面。有很多组很厉害，他会把这个答案都压得很小，可是不可能，我们自己做都知道不可能，因为我们的仪器没有这么完美。所以如果你把理论值跟实际值都做得很准的话，我们就觉得你作弊。就是我们自己做都知道，这个会有一点小小的误差，那有时候会很大，可能来自于3号就是会有一些问题。所以这个大家自己要注意。不过我们学流体力学就是这样，刚才我们所有的 exercise 都是理论上是这个样子，可是你实际上真的会有误差，而且实际上会有不一样的状况，代表你有一些假设不适用于实际状况。所以我们这一堂课学的都是理论。那大家知道理论就是你每次只要说出一个你想要为自己辩解的时候，你就会告诉他说理论上是这个样子，通常你下一句就是所以不是这个样子。所以理论的东西都很可怕，所以大家一定要在实验课的时候大概去了解这个状况。当我们说要打开这个闸门，我们说我们算这个 force， 我们就可以打开它嘛。你用这个例证去打开它，它没有开，那你这时候总不能告诉人家说奇怪，理论上应该要可以啊。不能这样子嘛。所以就是我们要去想一下那个范围，误差的范围。比如说我算出来是这个样子，那我可能要抓大个几%，抓大个20%，或者抓大个30%，因为会有误差，实际上会有误差。OK， 大概是跟大家讲一下这个观念。Okay, so we move to the final part. We call that the Bouillon Force. Okay, so it's based on the figure showing here. we discuss the ABC curvatures in here, and another we discuss the ADC conditions. So if I consider the ABC curve, we have the surface water loading, right? Because the ABC have the surface water loading acting on the ABC curvature. So we know that we have the gamma. For the ABC conditions, we have the gamma, and we didn't know the liquid material, so I use the gamma. And the total volume in here, we use the VA. So we know that if you have the gamma and multiply the VA, this is equal to the total weight acting on the ABC curvature. So this total weight is downward because it's a weight force. So the direction of the force is downward. Okay, so it is downward force. But if you consider the ADC curvature, so the ADC curvature, I need to have some supporting force. I need to have some supporting force because the particle just stop here. So we need to have some supporting force. Because this is a supporting force, so we think the supporting force is upward. So we have the upward supporting force. And how large of the supporting force? So I need to support the volumes from the A and the VB here. VB is the particle volumes, and the VA is the liquid column volumes. So we have a gamma multiply the gamma multiply the VA plus the VB. And then we need to make the balance because the force is up, it's the positive, and the force downward is the negative. So we make the balance is the gamma. The final F is equal to the F up minus the F down. So we put the F up is the gamma VA plus the VB minus the F down is the gamma VA, right? So only finally what kind of force you have is the gamma VB. So we call that the force in here equal to the gamma VB is our Bouillon force. So the Bouillon force is the relationship between the Bouillon force and depend on what kind of the liquid you use. So it's the gamma, what kind of liquid you use. And the second is the VB. The VB is the displaced area. Displaced area, like the material emerged into the liquid. So the displaced area is equal to here is the VB. We call that the VB is the displaced volumes. Okay. So the Bouillon force is only depend on the gamma, the liquid you use. And the second is the displaced volumes you have. Okay, so the FB is equal to the gamma multiply the VB. So this is just summarize the final terms in here. So if your particle is floating, so the displaced air volumes only have in here. Okay, not the total. So you need to figure out where is your displaced volumes and will equal to the weight of the displaced fluid. So the hydrometer designer, just based on this idea, just based on the Archimedes principle, and we can put the hydrometers into the liquid, and you can find out what the SG numbers you can read. Okay, so this is not important. So we have the one example to practice how to apply the Archimedes principles. So as the question, we have the two objects. The first object is the object one is the floating wood block. So this is the wood block, and the wood block has a specific gravity SG1 is equal to 0.3 here. Okay, so I write down here the SG1 is equal to, maybe I write outside. SG1 is equal to 0.3. Okay, and the dimensional is the 50, 50, and the 10 millimeters in here. Okay, so I can write down, I know that the dimension for the V1 is the object 1 volume is equal to the 50 multiplied by 50 multiplied by 10. So there is a millimeter cubic. Okay, so you can compute first, and the 10. So it's around the is equal to the 25000 and the millimeter cubic, and then we convert the millimeter cubic to the meter cubic. Okay, so it's equal to the 2.5 and the 5 minus 5 powers and meter cubic. Okay, and the metal part, the object 2 is the metal, and the volume is equal to 600 millimeter cubic. So we convert to the meter square is equal to the 6.6 10 minus 6 powers meter cubic. Okay, so please find the mass M2, the N2 of the metal part, and the tension T in the code. So I just plot the force body diagrams. So the first one, for the object 1, we have the weight. We have the weight downward, right? And we should have the upward force is the based on the Bouillon Force, right? So I use the FB1, 浮力, the Bouillon Force upward. And we should have the tension force along the line in here. So for the object 2, we have the upward tension force, and we have the weight W2 downward, and we should have another Bouillon force FB2 upward. So if I first consider the object 1, so I consider the object 1 conditions. I know that the FB, the Bouillon force 1, is equal to the weight W1 plus the T. Okay. So how can we compute the Bouillon force? As we know, the Bouillon force FB1 is equal to the gamma. What is the gamma in here? The gamma, because this is they put the, where is the gamma? So the example didn't tell us, but it's okay. So the environment in here the environment may be the water. So the Bouillon force, we need to compute the water gamma multiply the displaced volumes for the aperture 1. So you need to compute the displaced volume. So displaced volume 1 is equal to the area in here. So we have the volume in here. So how can we compute the volume in here? So we know the dimensional, the length and the width is the 50. The length and the width is the 50. So there is the 50 multiply the 50. But the height is different. The height is only have there is the 10 and the difference in here is 2.5. So there is the 7.5 millimeter. The 7.5 millimeter. So the unit in here is a millimeter cubic. So we need to convert the millimeter cubic to the meter cubic. So I use my calculator and convert to the meters cubic. So it's equal to 18.875 10 minus 5 meter cubic. Okay, so we can put the number go back to here. So it's equal to the water gamma is equal to the 9A110, the Newton meter cubic multiply the 1.875 10 minus 5 meter cubic. So we can compute the force. Okay, so the force is around the 0.184 Newton. So it is the Bouillon force. And what is the omega 1, the weight of the aperture 1? Okay, so because we know the SG in here, SG1 is 0.3. So the gamma for the aperture 1 is the gamma water multiply the SG1. This is the gamma for the aperture 1. And multiply the total volumes. So the total volume is V1. So we can put the number inside the 9A110 Newton meter cubic. Multiply the SG is 0.3. Multiply the V1 is 2.5. 10 minus 5 meter cubic. Okay, so you can compute the Newton. How large the Newton in here? So the 9A110 multiply 0.3 multiply 2.5. Okay, divided the 10 minus the 10 5 powers. So it's equal to a 0.0736 Newton. Okay, so we can make the balance so we can compute how large the tension force. So the topic in here, we need to compute the tension force first. So we know that the T will equal to the FB1 minus the omega W1. So it is equal to the 0.184 minus the 0.0736. So if you use your calculator to compute, the answer is around the 0.11 Newton. Okay, so this is our first answer for the tension force is the 0.11 Newton. Okay, and the second, we move to the aperture 2. So we move to the aperture 2. The aperture 2, the force balance is a T plus the FB2 will equal to the total weight W2. Okay, and So we already know the tension in here, and we can compute the FB, the Bouillon Force 2 first. Again, so we have the gamma W and multiply the VD displaced volume for the object 2. So what the displaced volume for the object 2? Because we know that the total volumes of the object in here is the 6,600 millimeter cubic. So we can compute the Bouillon force for the object 2 is 9A110, and multiply the 6,600, and we need to convert the millimeter cubic to the meter cubic. So here I use the 10 minus 9 powers. So the unit in here is the meter cubic. Okay, so we can compute the final answer. The 9A110 multiplied the 6,600 divided the 10 9 powers. So it's around the 0.0647 Newton. Okay, so and we know that the W2 is equal to the M2G, right? So we can make the balance. The tension force in here is 0.11 Newton, plus the Bouillon force of the object 2 is 0.0647 Newton, will equal to the M2. The G is 9.81 meter square second square. Okay, so we can compute the final. What the M2? The M2 is the 0.0647 plus the 0.11 divided the 9.81. Okay, it's around the 0.0178 kilogram, and you can convert the kilogram to the gram. So it is equal to the 17.8 G. Okay, so this is our final answers for the how large the object 2 mass we have. Okay, so the idea in here just we take the force balance. So in this example, we have additional force is contributed from the Bouillon force. Okay. So the idea is quite simple. We just consider the displaced volumes for our topic to compute the Bouillon force. Okay, so this is a very good example for our better understand how to apply the Bouillon force equations. Okay, and then the second, we have another example. We have the hot air for the in here we I may write down some figures. So in case we have the hot air inside, okay, and the hot air inside will have some provided the Bouillon force, so we can have some upward force. And the button, we have the people inside the button, so we have some weight downward. So there is we have some Bouillon force upward, and the Bouillon force upward need to overcome the people weight inside, and we also need to overcome some weight from the weight from the hot air. So we have the hot air and the weight from the people downward. Okay, so for this question, the three important, the first one is the people weight, and the second one is the weight from the hot air, the weight from the hot air, and how large can we have for the Bouillon force? the Bouillon Force. So we need to understand that some important parameter is the gamma air, right? We need to know the environment gamma for the air. And then we need to know the gamma hot air inside. So we know the gamma is equal to the rho G. And for the air, the density will change because the air can compress. Okay, so we need to answer two important parameters. First one is the density air. The second is the density for the hot air. Okay, because we discussed with the gas, so maybe we can apply the ideal gas law to compute the density for the gas. Previous example, we are always focused on the liquid problem, but this exercise we focus on the gas. So based on the ideal gas law, so we have the ideal gas law. So we know that the P will equal to rho R T, right? So for the environment air, so we have two conditions. Environment air, so this is environmental air. The P environmental pressures will equal to the low air multiply the air constants and the temperature air. Okay, so the low air will equal to the pressure air divided the R gas constant and the T air absolute temperature. So if you go back to see the example, we know that the pressure in here is 101.3 kilopascal, and divided the gas constant in here, we have the gas constant. So we write down the gas constant is 287 Joule divided the kilogram and the Kelvin temperatures. And the absolute temperature in here, we know that the air condition is 10 degrees. So the number temperature in here is the 283 Kelvin temperatures. Okay, so you can compute the air density. So 101.3 and 10�3 powers divided the 287 and divided the 283. So the low air is around the 1.247, and the unit is kilograms per cubic meters. So it's our first information, very important. This is low air. And for the hot air, so right now I compute the hot air condition again, so we can compute the low hot. What's the low hot? It's the pressure hot air divided the gas condition and the temperature hot air. So the pressure we have in here is the 120 kilopascal divided the gas constant again is 287 Joule kilogram Kelvin temperatures. But right now the temperature for the hot air is quite larger. It's 100 degrees. So here is the 373 Kelvin temperatures. So you can compute the low hot air. So I use my calculator, divided 287 divided 373. So the air become too smaller compared to the low air. It's 1.121 kilogram per meter cubic. So right now we have the low air and the low half inside the balloon. Okay, so we go back to consider our conditions. The first one, we need to compute the Bouillon force FB. As I mentioned, the Bouillon force is related to the gamma for the environment gas we use. So the gamma here, we need to use the gamma air because it is the environment gamma. The environment gas is the air, so I use the gamma air. And multiply the total volumes. So we know the volume for the ball in here. So this is our displaced volumes. So I put the number inside is 1.247. It's the density. It is the density air. Multiply the G is 9.81. And the displaced volume is 2,000 cubic meters. So I can compute the answers. 1.247 multiplied 9.81 multiplied 2,000. So it's around the 24466.14. Okay, and the unit is the Newton. Okay, and how about the weight? The weight of the hot air. We have the weight hot air is equal to, because we know that the hot air density is low half multiply the G, right? This is the gamma hot air, and the total volume is the same as the displaced volume. Okay, the total volume of the ball. So we put the number inside is 1.121 multiply 9.81 and multiply the total volume is 2,000. So we can compute the total weight for the ball for the hot air. Okay, so this is equal to the 2199.02 Newton. So finally, I only have one downward is the W in here is the people weight. Okay, so we go back to the final force balance. Is the FB to be equal to the hot air, okay, and plus the W, okay, W is from the people weight. So we know that W will equal to the two numbers shown here. We can just minus to compute the final answer. So the FB Bouillon force minus the W hot air weight will equal to, I use my calculator to compute the answer. So it's around the 2472.12 Newton. But our question is the total loading. So how large the mass we can support. Okay, so the final, we know that the W is the mass multiplied the G. So the M is divided the W divided the G. So it's equal to around the 252 kilograms. Okay, here a little bit different compared to the number showing here, but it's depend on the different low density we use. Okay, so that means if we would like to support the people weight is 252 kilograms, we need to control the different pressure conditions and the different temperatures. So you can control the different temperature, you will have a different density result, right? If we have a larger temperature, we have a smaller density. Smaller density, we can have the smaller air weight, hot air weight, and we can support the more people weight. Okay, so for像这种就是如果你是要做热气球的话，你一定要去设计好这个热气球可以支持你多少重量上去嘛。那另外一个是你可能可以改变气体，不一定要用空气。哦，你改变气体，你可以用比较轻的气体，比较轻的气体就可以更轻嘛，所以你的浮力可以支持更多人的重量。Okay, so you can decide based on you can replace the gas material, don't need to use the air, or you just increase the temperatures, and you can have a smaller hot air density. OK, 好，那我们先休息10分钟。